Hello friends, today we are going to calculate the support reactions of given propped cantilever beam which is partially loaded through 12 kN per meter of 4 meter of beam using Castigliano's second theorem. Now according to the Castigliano's second theorem, we have to first select the reaction which is going to be used as a redundant reaction, and assuming the support reaction RB as a redundant and going through the segmental part of the given beam as now for the CB section which is of 4 meter span, and if we assume the B as a origin, then distance of this section through the point B is as x. Similarly for A to C section which is of 3 meter span, and from origin C if we take the distance of section as a x and C to B section as a 4 meter, then moment in CB segment which is equal to RB into perpendicular distance as a x and 12 into x by 2 as a UDL moment, and the UDL moment is clockwise, and according to the sign convention, sectional right hand side anti-clockwise and left hand side clockwise, which is treated as positive, hence the clockwise moment due to the 12 kN per meter UDL is negative. So the sectional moment in C to B segment which is equal to RB into x minus 6 into x square. Similarly for A to C section, if we take the moment at section XX, then moment in AC segment which is equal to RB into perpendicular distance as a x plus 4. So RB into x plus 4. Now clockwise moment due to the 12 kN per meter UDL is negative 12. Now total load is 12 into 4. So 12 into 4 into, now CG distance from location C is 4 by 2, but we have to take the moment at section XX, and total CG distance is x plus 4 by 2. So the total moment at segment AC which is equal to RB into x plus 4 minus 12 into 4 48 into x plus 2. Now this moment is going to be used for the calculation of Castigliano's theorem, and the tabular form of Castigliano's theorem is as for C to B segment we have assumed origin as a B, limit of segment is given as 4 meter as the total CB segment is of 4 meter. Moment of inertia is taken as a I for both the span as it is missing in the example. Now for A to C segment our origin is assumed as a C, total limit of the segment is given as 3 meter. Now moment at particular section in C to B span is calculated as a RB into x minus 6x square, and for AC segment it is now going for the partial derivation, and according to the Castigliano's second theorem, strain energy at the location where deflection is 0 is also 0, hence strain energy at location B, as we assume RB as a redundant, then the mathematical equation is 1 by EI integration over entire span moment at section into partial derivation of this moment with respect to redundant as a RB dx must be equal to 0, and according to the superposition theorem, total strain energy at B which is equal to 0, which is segmental strain energy as a UCB and segmental strain energy as a UAC in span A to C. So we have to calculate strain energy according to the equation of Castigliano's theorem for both the term, and going for the partial derivation which is del mx by del RB, hence for C to B segment RB into x minus 6x square with respect to RB which is as x, and for the AC span RB into x plus 4 minus 48 into x plus 2 with respect to RB which is x plus 4. Now going ahead for the calculation of strain energy for both the segment, as for segment C to B If we use the mathematical equation, then it is 1 by EI integration limit as a 4 meter, hence it is 0 to 4. Now sectional moment is RB into x minus 6x square, and multiplication with respect to partial derivation is x, hence multiply by x. Now going ahead, 1 by EI is constant, integration limit is 0 to 4. Now RB into x as a RB into x square, and minus 6x square into x as a 6x cube dx. Now integrating this term with respect to dx, we will have RB as a constant as a reaction, x square dx integration, which is x cube by 3, minus 6 is constant, x cube dx integration as a x raised to 4 by 4, and integration limit is 0 to 4. Now closing these limits, we will have RB into x cube by 3, which is 4 cube by 3, and EI is constant, minus 6 into 4 raised to 4 by 4 EI. Hence our strain energy in C to B segment, which is equal to 21.33 RB minus 384 by EI as a strain energy in C to B segment. Now for A to C segment, we have strain energy in A to C segment, which is equal to 1 by EI integration limit of 0 to 3 as a segmental distance is of 3 meter. Now moment at section is RB into x plus 4 minus 48 into x plus 2, and partial derivation is x plus 4 dx. Now multiplying x plus 4 with the moment, we have here RB is constant, and multiplication of x plus 4 with the x plus 4 as a x plus 4 whole square, and it is treated as a square plus 2ab plus b square. Hence x plus 4 whole square as a x square plus 8x plus 16. Now minus 48 is constant. Now x plus 2 multiplied by x plus 4, which is x square. Now 2 into x as a 2x, and x into 4 as a 4x. So 2x plus 4x as a 6x, and 2 multiplied by 4 as a 8. Now integrating this term with respect to dx, we will have RB is constant. Now x square dx integration as a x cube by 3 plus 8, x dx integration is x square by 2 plus 16, constant dx is as a x, minus 48 is constant, x square dx, which is x cube by 3 plus 6 constant, x dx integration as a x square by 2 plus constant integration as a x, and limit is 0 to 3. Now closing this limit, we will have here 1 by EI is constant for all the term, rest value is RB is a constant. Now x cube by 3 and upper limit is 3 as a 3 cube by 3 plus 8 into x square by 2 as a 3 square by 2 plus 16 into 3. Minus 48 is constant. Now x cube by 3 as a 3 cube by 3 plus 6 into x square by 2 as a 3 square by 2 plus 8 into 3. Now solving this term, we have strain energy in AC segment, which is equal to 93 RB minus 2880 divided by EI as a strain energy in A to C segment. Now we know that the total strain energy at location B, which is 0, and it is summation of strain energy in C to B segment plus strain energy in A to C segment. So summation of UCB plus UAC, which must be equal to 0, hence 0, which is equal to 21.33 RB plus 93 RB, which is equal to 114.33 RB. Now minus 384 plus minus 2880, which is negative of 3264 divided by EI. Now solving this term, we will have redundant reaction RB, which is equal to 28.55 kilonewton. So using Castigliano's second theorem, by assuming redundant reaction, we can calculate that redundant reaction using this mathematical calculation. Now going ahead for the final reaction of given beam, as per the above calculation, we have calculated redundant reaction RB as a 28.55 kilonewton. Now vertical reaction at support A as a RA and anticlockwise moment as a MA, then taking the equilibrium condition sigma vertical force equal to 0, we will have vertical reaction RA plus vertical reaction RB, which is 28.55, which must be equal to downward load and total downward load due to 12 kilonewton per meter UDL, which is equal to load into distance. So it is 12 into 4. Now solving this term, we have RA which is equal to 19.45 kilonewton. So our reaction at support A is 19.45 kilonewton. Now going ahead for the equilibrium condition, sigma moment at any location equal to 0, and if we assume the sigma moment at A equal to 0 and treated anticlockwise moment which is equal to clockwise moment, we will have the clockwise moment due to the 12 kilonewton per meter UDL, which is load into distance into CG distance is as a 4/2, but we have to take the moment at location A, so plus 3, so 4/2 plus 3, which is clockwise, and anticlockwise moment as a MA, so equal to MA plus RB into total distance, which is 28.55 into 7. Now solving this term, we will have the moment at location A, which is equal to 14.15 kilonewton meter. So using the Castigliano's theorem, we can find out any redundant reaction as assumed reaction, and after that using equilibrium condition we can find out the wall reaction of given propped cantilever beam, which is a indeterminate structure. Thank you.